So, hello everybody, let's get started. As I wrote, I thought, several of me asked me to talk a bit about high-throughput sequencing, which is of course sort of one important application of biostatistics these days and also of bioinformatics. And I thought I'd just show you a standard RNA-seq analysis. There's three parts which you have to talk about when you talk about RNA-seq data analysis. One part is the whole data pre-processing. Which programs do you use? How do you run through them? How do you battle with the command line? Part two is, of course, the data interpretation. What kind of biological questions can you answer and what you cannot? And the third part is the statistics. What do you have to understand about the statistical side of your data analysis in order to be able to actually know whether your biological interpretation makes any sense? The last two parts are also connected in the point that if you plan a high-throughput sequencing experiment, you want to plan it well because it costs some money. You want to understand what you can actually achieve with this. And there's quite some mistakes often made there. Now, I thought that for today I will focus on the technical aspect. The technical aspect is in a way the most boring of it. It's just putting a lot of commands in front of each other and battling with your computer, but you have to get through and you have to get a bit of a feeling for that. So we'll rush through it so you've seen it, that you've seen the whole process from starting the reads as you get them from your sequencing core facility all the way to some first plots. We will probably not manage to come to a point where we then can try to make some biological interpretation of this. Maybe we can talk about this next time. And the statistics, I'll talk a bit about the statistics sides on the side, but I won't get too much into detail because for that we have to talk about ANOVA, which is a subject that's also of importance outside of high-throughput sequencing. And this I think we can do next time. I could give you now a grand overview of what kind of sequence you can do for what, but I thought I'd just jump in the middle of something and just demonstrate a typical workflow and go through this. Before that, who has already worked with high-throughput sequencing data? It's actually not so many. So, now some of you might know that the thing which actually sort of boosted my own career was the development of a tool called DE-seq, which is one of the standard ways how to analyze RNA-seq or transcriptomics data. And I'll show a bit, but only towards the second half of today's hour, how to use that one. And we'll talk. Maybe we can talk about that and alternatives and so on. But let's now see where we start. Of course, I've given many courses on DE-seq, and our standard example for a data set that we always use to demonstrate this is from this paper here, which is from 2014. You see it's a +1. That's already a little point that you can see here from the fact that it is a +1. They didn't get really to very deep conclusion. You already see this in the abstract where they say we have found 316 differentially expressed genes, which a few of them were known and a few of them were not known, but we don't know what they mean. This is the standard outcome of, I think, 90% of all high-throughput sequencing experiments. That in the end, people get the list of genes and they ask, so now what? But this makes it a typical and normal example, and it's a simple, small, boring little study. Maybe not that boring if you find something in it, but we'll just use it as an overall general thing. I should now hasten to say, actually, I've never really read this paper thoroughly, so maybe I'm unjust to them. They came to a lot of very clever conclusions in the end. I only, because I always give the course and I always just want to use their data as example to discuss pre-processing. So I've never really looked into what they did in the data. Maybe there's a lot on it. So what can I tell you about what they did? As you can see from the title, we are talking about airway smooth muscle cells. What's the point of airway smooth muscle cells? Well, the muscle in your airways are the muscles which constrict the airways in case of an asthma attack. So in order to treat asthma, you use compounds which either stop the immune response, so a glucocorticoid, or you use something which relaxes, which causes the asthma to relax. So their idea, which actually is a very neat one, is that they took muscle cells from 4 male donors, so just muscle cells which they took from the trachea, if I understood correctly, and these trachea cells, they made a cell culture out of them, and then they treated them with 2 commonly used drugs, namely dexamethasone, that's a glucocorticoid, and albuterol, that is, I've just looked it up, it is actually, but it relaxes the muscles, and it seems to be the stuff that is in these asthma sprays that asthma sufferers always carry around with themselves. And now they said, let's just put these cells onto these 2 drugs onto our 4 cell lines and see how they react and which genes differ if we take the transcriptome of these cell lines before and after treatment with either of the 2 drugs or with both drugs in combination. The thing which probably might be the problem that they had is, and that I now again speculate without having read it properly, which might have caused them to end up in +1, is they used 4 cell lines, which is a very good idea because they reasoned that maybe not all people are alike, and if they now use a cell line or a tissue culture derived from one patient, they might find out a lot of interesting things which are not true for asthma in general, but just idiosyncratic to this patient. So of course they used a combination of 4 cell lines, which of course risks that the 4 cell lines from 4 donors will give you 4 different results, which is good to know, and which is very good for pharmacological consequences, because when you know that these things are not a good way to find drug targets, but it makes publication more difficult because you actually know that you've done mistakes. But I highlight this here because I think it's actually a very good idea to, if you do something like this, that you do it not on one model system, but on a couple of model systems with different genetic backgrounds. So how would we now proceed if we want to go ahead and run this data? Where is the full text here? Here. What we typically have, as you might know, when for most journals, if you want to publish any high throughput sequencing data, you're required to put this data on a public archive for short reads. There's the short read archive run by the NCBI, and there's the European Sequencing Archive run by the EBI. They somehow copy their stuff around, and they both, what they both have in common, that they have an insanely complicated database structure and complicated web archive, and nobody ever knows how to download anything from them. So this is why I now really start with that part. Here we find up. Now, where is here we find where RNA seq is available from GEO under accession has been moved. What happened here? Just a second. Under this accession number. So let's copy the accession number, go to GEO, put in the accession number here, search it. Now we find it here, and here is all the samples. We can click on a sample here, and we get this all kinds of use of interesting information which tells us what it is, and you have to fill out loads of web forms if you submit these things. So of course nobody wants to do that. It's also not so helpful, but what you don't find is the link to download the whole data, which I think is here. SRA for short read archive. I'm not sure how anybody should know that you have to click at the link labeled SRX to get your FASTQ files, but believe me, I spent a while to look for this. Now I go on this, and now I find something which is called a run, SRR, and now I get here this whole run, and yeah, it says download, and then it tells me that I need a toolkit. So what have I done in the end? I went here on all the samples, then I somehow found the series file. Now it's possible that I now won't even manage to find this again, because I went to the short read archive, where I went to the external link, and in the end, I don't believe it, I actually don't think I'll manage it anymore. Untreated sample study, here it is, all experiments in this study, and then I get the list of the 16 things they have, and then I can click here on this run selector, which is somehow new, and now I get here the list of their run numbers. Now if I have the run numbers, I can do the following. If I have one of these run numbers, for example, Ctrl+C, I can download, install something which we call the Short Read Archive Toolkit, or SRA Toolkit, which contains a tool called a FastQDump. So to do this quickly, I show it to you here. Let me go to my temporary folder where I just put stuff. So I use this FastQDump. Put the run number, and if I now press enter, it does something and complains because they recently updated their whole data, but I've installed it here. cd sorry about this. cd/aux. So what I do there is, I might now say FastQDump, and we I've written it twice, and it will start dumping my FastQ file onto the screen. At least I hope so. Now it produced here a CD. I'm getting them. Maybe that's even not that useful. The first trick that I wanted to show you at this place here is, you might notice here I'm working here on my command line, which is usually quite helpful. What I wanted to do here is use this FastQDump file and run it on all the different short read archive things. And this of course means I have to issue 16 commands. I don't want to copy and paste all these things. So I used here my the list of all these runs and used my favorite text editor, which has let me download this thing. Run info table will need accession list. We'll need this thing more often afterwards. Here now I have this accession list. I copy it, use my favorite text editor, which has this useful block editing feature. See here, and type FastQDump -- split files in case you ever need this. You will need this and put this, and when I copy the whole thing, yes, of course it's important. FastQ, and now I can take this whole thing, go over to my command line, just copy and paste it here, and it will execute all these commands in one go. And when I go for coffee, and when all this stuff is not there, it actually took 3 hours to download this stuff, and when I still wasn't finished, and when I lost patience and thought, okay, I'll demonstrate this to you with the files which I've downloaded that far. So what I got is, when I did it yesterday, I got these FastQ files. And now, what is a FastQ file? Let's have a look into it. Who has already worked a little bit with the command line, by the way? Okay, all the others will now notice most of these things you could also do with your usual with your usual, I think the Mac people call it Finder, or the Windows File Explorer here on Linux is called the Nautilus shell. But I prefer to do it here, and you will probably now by watching me realize why it is faster, even though you can't quite plain it. ls means list the content of this directory. At the moment we are in this directory, and ls means listed. Here we have the file names. ls minus l means listed, including all the extra information like how big they are. ls minus lh tells us an easier thing. You see these are several hundred megabytes. If you try to open any of these files in a text editor, or in Word, or in whatsoever, your computer simply crashes. So you need a tool which allows you to really open giant, large text files. This is very important. I've got it quite often when newcomers, I have a big text file, and I ask them what's in there, and say, sorry, I can't open it. Especially if you're a Windows user, you probably won't have any tool which opens it. This is not a valid excuse. If you don't have one, get one. You really need to be able to look into every single file which comes out of your data. On Unix-like systems, which includes the Mac, you always can use something like the command less, and the less command, which has a strange history why it's named so. This was some kind of inside joke of 40 years ago. Allows you to look into these FASTQ files, and now you see here how this file looks like list, and it goes on like this for millions of lines. Now, in each read in a FASTQ file has 4 lines. The first line is the so-called read ID. In this case, it's read ID from the short read IRIS and so on. Often it is the serial number of your Illumina sequencing machine plus the spot where it was in flow cell. This is the actually interesting thing. That's the sequence where it was read. This is just a repetition with a plus, and this is what's called the quality string. The higher the number, the more surer the sequencer was that it has read the base correctly. D, for example, is a high number. A exclamation mark is a low number. Why is an exclamation mark a number? Well, you might be aware that there's something called the ASCII table, which is the way how each symbol is assigned to a number. And here you see how these symbols go. First go from exclamation mark and so on, and then come the numbers, and then come the capital letters and so on. So this is how this is stored. We don't need that so much. The important thing is that this is how your data looks like. You can get a first look by looking at the quality scores and say, okay, J is a high number. This, for example, is a good read. That's what you want to see in the most of the stuff, but not all of them. So you might have a quick look through all of this stuff. What you can also do is you just go ahead and align the thing to the human genome. After all, this is human data, so each of these reads is expected to appear somewhere in the human reference sequence. So the way how you do this is you use a short read aligner, which is a high-performance computer program which goes through all of these reads and tries to find where they are in the genome and report this. We do this using something, for today I've decided to use an aligner called the SFB aligner, which is done by Gordon Smythe's group at the WHI, that's the William and Eliza Hall Institute in Melbourne in Australia. And how this thing works is you write something like, and I now show you how the alignment command looks like, SFB align. And always in all these command line programs, usually if you just type them like this, they tell you how to use them. It's a long thing, so if we read from the beginning, SFB align the options, then the index name, then the input FASTQ, and then the output. Now, what is an index name? The aligner has to prepare for aligning to the human genome. So we take the human genome. So it needs a big file which is used to which tells it which kinds of sequences appear in the human genome. In that case, because the SFB uses something called a seed and vote strategy, it always takes short pieces of 10 sequences at a time and checks where this is. So for all possible 10 MERS, it has a table where they appear in the human genome, and we first have to make this table. So we say, see if it's still in my SFB build index. Yep. Here we are, still are. Another nice thing of the command line, you can press Ctrl R and go back to your old commands. And you see here, I use this file for the human genome, and this is how I call it. And then it produced this. So what is this file? Homo sapiens CRCH38. It comes from Ensemble. Yeah. We come to this in a second. So first we need a human genome. Where do we get a genome from? We go to Ensemble, go here to Downloads. There at the download we have a lot of fancy colorful things which all have nice picture, and then there's this boring thing here at the very right, download data via FTP, which is the only useful link on this page. And there we find now Homo sapiens DNA. Here we now find files with all the DNA of the human genome for each chromosome separately, and one for the whole human genome assembly. So this is your primary assembly. I download that one. You remember the trick maybe already from last time. I say copy link address, and I can Ctrl C, write wget and Ctrl V and the link address, and then it will download this file. This takes about 3 minutes, so I won't do it, as also because it overwrites the thing I've already downloaded. But this way it would download it. And the next thing you see, it ends on GZ, which means gzipped. So it's compressed. So we need to unpack it to unpack a gzip file. Of course, we need gunzip. And then you write here the name of the file, like this here, and it will replace this with an unzipped file. And I have already done this in preparation, and so here you now see the unzipped file. Again, this is a huge file. You see here 3 GB. So let's have a look inside, because we are not afraid of huge files. Yeah, this is chromosome 1. As you can see, it starts with a lot of N's. Why does it start with a lot of N's? Anybody knows? Exactly. We list the chromosome is usually given from the telomere of a short arm through the centromere to the telomere of a long arm. Sorry, the other way around. We start with a long arm and then we end with a short arm. And so the first couple of things are N's. This is just telomere. Now we come to a bit of repetitive part of the telomere. Now comes a bit sequence, and now we are getting all the way into it. At some point, now I'm probably in the centromere, and so on. If you want to get out of less, by the way, I press Q for quit. I can also search and replace, and then you see there's such a thing for chromosome 1, another one for chromosome 2, 3, 4, 5. An important part, which is really something that can cause you hours of searching if you don't know it, every time every 2 or 3 years, they make a new genome assembly. Genome assembly means they take all the contigs that they've sequenced and try to puzzle them together to form the full chromosomes. Of course, if we now sequence a bit deeper into the telomeres, or if they decide some indels which we've overlooked before, all the stuff shifts. So all the coordinates in the genome will shift. So it's absolutely essential that you always know which genome version you're working with. This here is version CRC, Genome Research Council, Human Genome version 38. If you ever lose track of that, then you'll get into deep trouble. This is why I leave it in my file name. And now that I have this, I have to build my genome index, and I say here subread build index. It tells me how to do that. I should first give this genome a name, and obviously my name is GRCH38, so that I'll never forget what this is. And then the FASTA file, which we just had. DNA primary assembly FASTA. Now I would press enter and it would produce these files, and this would take a couple of minutes. And then I get, then it produces these files, which last time I put them here into index. Here you see CRCH, and Again, these are huge files, 4.9 gigabytes and so on. And then once we have all this, we can now try to align our genome. So for example, I could do separate, align. Again, now I need to fill out all these things. First the options, now the index name. What is the index name? This is where I put all these index files here. In the subdirectory index, all the files whose names start with CRCH. Next, we are supposed to give the reads, -r. You see here it says -r, the faster or fastq or whatever. So where's my reads? I had put them here in reads, and there you remember there's all these files, and I take the first one. This is paired end data. Everybody is familiar about all these things about paired and single end? Who doesn't know about that? Okay, seems you all know this thing. So, or did somebody mark up? No, I didn't see anybody daring to show off that they don't know that. If you really don't know and didn't care, just fragment the DNA, or in this case our RNA will get fragmented when we reverse transcribe it into cDNA, and when we have cDNA pieces which are about 300-400 base pairs long, and we sequence inwards from either side. So now we have here our FASTQ file, and we have to give it the other one for the other end. So this was the first end, this is now the second end. I get it out like this, and what do we want next? We are supposed to give an output file where it should go. For reasons which I explained to you afterwards, these are called BAM files, the output files. And then the last thing is it's supposed to have here -t a type, which is 0 for RNA-seq data, -t0. Then I can also add a lot of other options which are in here, if you really want to know them. But one reason why I like the separate aligner is that it has really good documentation. There's a 40-page PDF thing on the web which explains all the stuff in detail. But this way I would now simply start it, and if I start it, it writes here a nice separate. It now reads in the index, and in the end you get some result, and it takes about 20 minutes to align this stuff. The important thing that you might have already noticed here, this read ID 10390558, that appeared 3 times in this command, and it's very important to not mix it up here, because I have now to type this command for each of the reads. And what I did in the end to solve this is that I wrote myself a little R script, and I can show you this afterwards, which just produces this string here. I can actually do this in R. So, where was it? Here. Now let's go to our R session to not forget that we still have R. So, this is our read command, and what we can now use here is the string interpolate function, which is a string interpolate. Let's simply do it like this. Let's say we have let's simply use string concatenate, and now you see how this command works. It starts here all the way like this, and then comes here the run ID, and the run ID should then be followed by _1.fastq. Then we have a run ID again. Ctrl+C. Run ID is this. Now I have that one again. Run ID, comma, and this part, and again the run ID. And then that last part. And we want to concatenate it all. So I now say this, and now it gives me out the command as I want to have it. Now maybe I have a list of all the run IDs, which I could maybe have read from this file, which I now somehow have misplaced. But let's say it simply looks like this. And now run IDs. And now I can use something like this map command, which you might remember from last time. We want to map stuff, and we want to make sure that in the end we get a character string out. So this would be our make command function. It's a function which takes a run ID and produces the command. So if I write something like this, then it will now make me here this thing here with xxx1 fastq, xxx2 fastq, and the output should be xxx dot bam. And if I do this like this, then I get my command. And if I now use the map command, which tells me please call this command here for all of these run IDs that I've put up here, I now get all these commands here. And having all these commands written there, now I can either just copy and paste them in my command line, or I can also write them out by giving this to the write lines, not block lines function. Align dot means shell commands. Yeah.
I got confused. What are we doing here? I mean,
At the moment we're trying.
no, I mean, yes, here you align, right?
We're aligning, but we need to call the aligner here. This is the command which I have to issue for each read, and I have to issue now 20 commands. So what I now do is I write this command, and now it has produced a file which is called align.sh. And if I now open that one, where has it ended up here, you see it contains these alignment commands. And now the advantage is if you later want to go back and are not sure anymore, because the worst which could happen to you is that you swap any IDs in here. When you align the fastq file 939508 and write it down in the output file 395010. And if you have any swaps, so it's important to not try to do this by hand. So you want to write a little code like this, which produces all your commands, and when you have them here, and then you can just execute them. And if you write them all below each other in one thing, and then give them to your command line, just taking it and let's say just pasting it here, then what will happen is actually that they just all get executed one after the other until it's finished. The aligner will run on the first thing, will run for half an hour, then it do the next one, and when you go, you start this in the evening, when you come back the next morning, everything is aligned. A lot of people usually think that you need big computers to do high throughput sequence analysis. That was true when Illumina sequencers were new 15 years ago, or 10 years I think. Nowadays a laptop like this can do this without any problems. The important thing is you want more than 8 gigabytes and you want a big hard disk. But that's really all we want. So as I said, these aligners, they produce a file which is called a BAM file, and we should have a look into these BAM files. So the last time I ran this in preparation of the course, I put all the BAM files here. So this is what the alignment command produced after I ran the alignment command and all this stuff. And let's look in one of these BAM files, because as I said, let's first see how big they are. They are again several hundred megabytes big. I again use less to look into them. It says it may be a binary file. See it anyway. The reason why it asked me is because it looks like this. This is not useful. Actually, a a general trend in bioinformatics is that people try to use text files, so files into which you can look into with less. So far we have been able to look into everything. But these files are so big, so they need to be compressed, so they can be switched from a text format back into this format. So I can use the samtools view command, which of course I first have to install this program called samtools, on this BAM file. So SAM, by the way, means sequence alignment or mapping format. BAM means binary sequence alignment or mapping format. Why it has alignment or mapping is something which you have to ask Richard Durbin and Lee Hang at the Sanger. They had a lot of strange ideas with this format, but now we are stuck with it. So if I say samtools view, then it will put these onto my screen. This is of course too quick to see them. So what you always do on the command line, we use this pipe symbol. So you already notice what I'm doing here now. I rush you through different little things about the command line, which by itself won't quite help you to really then use the command line yourself, but give you an overview of what's out there and what you have to learn. And then at some point you have to find the 1 hour to read one of these introduction to the command line tutorials. But you already now know where the whole thing is going. Less, as you've seen before, is a tool to look at big files. So I can ask, take the output of this thing and give it to less. And the pipe symbol always means take the stuff from the left command and give it to the thing on the right command. And now I can here move up and down with my page up, page down keys. And you can see how this changes. And Q again to get out. What I also add here is an option. All these commands have options and long lists on the internet or on the help pages about what the options are. What is -S? It's this here. It makes the lines on one big row, because afterwards they were broken because each line was too long to fit in there. Now this is a bit hard for you to see, so I hold it up. I can go up down in this thing, and I can go right and back left. And this is now how the SAM files look like. This is what the aligner produces. So let's have a look. It tells us this here's the read ID. So the first read in the FastQ file was had a flag status of 99. I now won't get into this, but at some point you will probably need to learn it. It was, and the sequence was found on chromosome 7 at this position. And we reversed, remember we sequence each fragment from both sides, so the other end was also found to be mapping to chromosome 7 to this position, which as you can see is a little bit, namely 227 base pairs downstream, which makes sense because the whole fragment should be around 300 base pairs. Here we see the sequence and the quality string again, and here see a little extra flags. For example, the important one is this NH, which tells us how many mismatches there were and how many alternative places there have been to find this thing. What you really want to know, of course, is now which genes were expressed. So how do we get to gene expression? We need to now look up for each of these reads whether it falls into a gene, and then say, okay, we have seen one read from this gene. For this we need a list of all the genes and where they are on the chromosome. So we go back to Ensemble, to the FTP download page, and then the next one, you see there's lots of things, and most of them I've never looked at. The only two I ever use is here, DNA, and here GTF. I go on GTF. They seem to have all different names. I just decided to take the one with the simplest name. This here is again version 38 of the chromosome assembly and version 94 of the gene annotation, so of pinpointing the beginning and end of the exons on the genome. I've already downloaded that one for you and put it somewhere here. Let's have here this one, and we look into it, and now again I should use my -S to make these broken lines nice and long. And here you see how a GTF file looks like. It has on chromosome 1 there is a gene called 22387 or DDX11L1, which goes on the plus strand from here to here. And this gene has several transcripts, and each of these transcripts has here 3, here 6 exons, and so on.
What's the second column for the Havana column?
Nobody knows. So a part of the problem with these gene formats is when this whole thing was young, a couple of people decided to just set up a database and make this data downloadable. And of course, the ensemble people made one format, and the UCSC people made another format. If you write software which has to do it you have to explain to the software. This time, the start of the gene is on the is in the third column, and next time it's on the fifth column. And this time we are counting the gene position starting with 1, and next time we start with 0, and sometimes the end is included and sometimes not. And then they started to try to agree on things and try to make some general superset of this whole thing. They concluded a lot of columns which somebody put there and then nobody ever used. For example, for some reason everybody agreed that the type should be in the third column and we start in the fourth column, and nobody could remember what we put in the second column, so we call it source. And here it now tells you, and this makes sense because Ensemble at least seems to use it to tell from which of the various databases they pulled it. From the Ensemble main database, the Havana database for curated stuff, the Mir base for microRNAs or whatsoever. The GFF and GTF formats were especially notorious for and this is something which, if you're a bioinformatician and spend a lot of time programming such stuff, you really get angry at these people who managed to, for a while, the UCSC and the Ensemble couldn't quite agree on whether these intervals are end included or not. So if you have a gene starting at position 1000 and it has a length of 100 base pairs, then of course the first one will be 1000, the last one will be 1099. But programmers like to indicate as the last one 1100 because then you can just say end minus start is length. So both has its standards. For example, in R all intervals are end included. In Python all intervals are not end included. So half of all languages do one, half of all languages do the other. The same way, or half of all languages count their start positions from 1, others from 0. So obviously everybody who's a halfway competent programmer or software developer knows that whenever you give any kind of index, the first two questions you have to answer is it 0 or 1 based, and is end included or not. The heroes of the Sanger and on the EBI Institute managed to need, I think, 8 years to finally clarify this on their web page. Before everybody always ran around, and I think of the GFF format we now have 2 variants. One is end included, the other isn't, and that is only not because people couldn't agree, because people forgot to write down what they agreed on. It annoys me because it actually has personally cost me many hours of headaches. Anyway, so what do we now do? We have this GTF file which tells us where the exons start and end. We have a BAM files which tells us for each individual read where it goes. So what we now do is we use a program to bring these two things together. In our case, I use the feature count program, which is also from the VHI people. Here again you see the usage. Feature count, first the annotation file with -a, then the output file where you want to put it, and then the input file. You might wonder, why do we do it this way around? Well, the reason is, what we can do is we write feature counts. Now the annotation file, where it's this GTF file. Now the output file, counts.txt. And now the input files are all the BAM files I want to do, something like alignment / all these files which start with the stuff and end with BAM. And what will star means everything which sort of fits this pattern. And now, if I now started this, and I don't want to start it again because otherwise we stand here and actually only wait for 5 or 10 minutes. This program is amazingly fast, cutting through all these magnificent things. When what it produces you in the end is these two files. Feature count out. Let's have a look into it. And here you see how it looks like. For each gene, it has the gene ID, then on which chromosome it sits, where it starts and where it ends. You see this gene starts at 3 different positions and ends at 3 different positions. Probably it has several isoforms. And then now for each of our 8 samples, the column, which is this, which now tells us that this read here has 74 genes sequenced to that one, 114 to that one, 90 for this, and so on. If we do this, and now finally, we can go back to R and actually read this stuff. So I've already prepared this a bit, and we'll probably have to go next time through the exact analysis. So for now, let's look at what I've done here. I load the tidyverse, you already know this. And here, this is this feature counts file. How would I import it? I go here, import dataset from base R. Now this still works as bad as last time. Here, feature counts out. And here you can, really can't see this. Try it yourself at some point. The important thing is you have to tell it that it uses tabulator things as to hit the things, and that the comments is a help here. It's that thing. And in the end, the read import data thing tells you that this is the command you should use. We want to read the file feature count.out. The different individual columns are separated by this tab character, which I remember I've never really explained what a tab is. But it's supposedly the thing which happens if you press the tab key, and any lines which starts with a hash sign is a comment. Where was this? Here you can see this. The first line starts with a hash line. That's a comment. It just tells us, and that's quite useful, what command we have issued, so that you can look it up. And then we have here the column names, and always from one column to the next. There's a tab between. Here's R. Now if I read this, let me put this here out of the way. You see here now how my file looks like. I have gene ID, chromosome start and strand length, alignment SRR the first, the next, and so on. The way how I now did this is that I only select, let me remove this one for the moment. I only select those files which start with a I first show you what the whole thing is. The whole thing changes the whole thing to a matrix. You might remember this from last time when we talked about heat maps and said the tidyverse is nice, but a lot of stuff in R still work the old-fashioned way, and where you work a lot with these matrices. And here now I have a matrix, counts matrix. And if I now look at the first 5 rows and the first 5 columns, I see how this matrix looks like. It has here the gene IDs. Here it has the column IDs, which are the run IDs, and it puts them together. Here is how I did this. I run all this thing, and it first says the column labeled gene ID should become the row names of my matrix, like this here, and the columns labeled SRR, and I only want those columns which start with the word alignment. And why does it actually? Oh, it has an error. Find inherited. Not that again. If you ever get that one, for reasons which I really don't want to get into, you have to say desired double colon. So now I get it, and here you remember it has this alignment slash in front for strange reasons. So let's practice another little thing of R. How do I get rid of this? what I'm looking here is at the column names of counts matrix. These are the column names of a count matrix, and you see these are simply the file names. And because I executed my feature counts command being in one directory, and the reads were in the subdirectory alignments, the name of the subdirectory is in here. These are the things which are easy to fix in R. I simply say, take this list of column names, remove from the string remove the word alignment. As we add it, let's also remove the word BAM. And now write this back into the column names of the matrix. Now our matrix works normal. The other thing that we need is we need a run table. The run table was, if you remember here, this is the run table. And the run table contains something very important, namely here the treatment column, which tells us which run actually was treated with the drug and which wasn't. So I took this thing here, clicked some here on the run info table download table, and when I click on that, it downloads here this run table, and I put it here. I think I renamed it to the word run table, and now I read it. I get this lengthy table with lots of useless columns. Decide actually all I want is dplyr. Next time I explain where this now comes from. All I want is these three things: the run, the cell line, the treatment. And then I thought with treatment I don't like how it's done. Untreated dexamethasone albuterol. Often when people like to do this, they like to have a column which says dexamethasone plus minus albuterol plus minus. So I do the same here by saying mutate, make a new, remember mutate means change a column or make a new column. The new column should be called albuterol, and if we detect in the treatment string the word albuterol, then it should be yes, otherwise no. Here you see, and now I have a new column, albuterol, yes, no. Mutate, and you can also see how this whole thing works. String detects this word in the string and gives either true or false, and our if-else statement then changes this to yes or no. And if I now do this all, I get my run table, which now looks like this and is quite easy to work with. So this was now all the preparation to get stuff in. What do we do next? I now quickly run through the rest, and next time we look at it in some more detail. I load my DESeq package, or maybe I should say Mike's DESeq package. I've written DESeq 1 when I started my postdoc, and then we made DESeq 2, and we means I made a lot of clever remarks, and Mike loved it, the actual work. And the way how DESeq 2 works is it has this idea which is typical of bioconductor. For those who don't know bioconductor is an initiative trying to get packages for R which do biological or molecular biological tasks and bring them all back into one big repository, and where they all are tried to brought into shape that they easily interact with each other. This bioconductor package, this whole bioconductor project was founded by now 15 years or so, when expression microarrays were new, and founders were among others Robert Gentleman, who also developed R, and Wolfgang Huber, who was my former postdoc advisor, and a couple of other people. And bioconductor has a few principles, and one of them is we try to bring all the data into one central part. So here, for example, I make one object which is called DDS, which now contains all the stuff we need, namely both the counts matrix, which tells us the individual counts, and the run table, which tells us for each table for each column of the counts matrix what we know about this. And they are now all in one object, which is called DDS, just for DESeq dataset. And here you see it is an object with 16 samples and 58,000 genes. it has here all these gene names which are samples and all these sample names which are called like this, and it has extra information on these samples which are called run, cell line, treatment, and so on. Now this is worrying. Let's hope we don't need the internet anymore today. The design is something I have to explain in considerable detail, because this is now a crucial point. This is the question we're actually asking to the data. And in that time, I first thought for a simple start, let's ask a simple question. And this question is, which genes change their expression under dexamethasone treatment? So I only want to compare the dexamethasone to the non-dexamethasone data. To this, I use this here, this subsetting. You already have known the subsetting before when we subset a matrix, and in a way this still is a matrix where each row is a gene and each column is a sample. And I want to know, and here this tells us, as you remember, which of these samples are albuterol treated. And I only keep those which are not treated with albuterol, because for the first thing we want to ask a simple question, only use one drug, so we don't have to think about how to look at the interaction of two drugs. Of course, that might also be something interesting to look at, but one thing after the other. So by DDS, as you've seen before, is a data set with 16 samples. And if I now say take only those samples where albuterol is no, then I get one with only 8 samples. And I call this DDS DEXA. If I subset this way, then I automatically subset both the count matrix and the run table, which is a useful thing to make sure that we keep the things together and that the run table still aligns nicely with the count table. Again, this is terribly important because you have to make sure that your run table and your count table don't get disconnected. Imagine you would delete the first sample from the run table and the last column from the count matrix, when all the indices shift by one, and suddenly your treated samples become the untreated and vice versa. These things happen amazingly often and amazingly quickly. This is why tools like the bioconductor infrastructure take so much care to always force you to bind everything together and then lead it in one way. So now I have this thing, and I now specify my design, the question which I want to have. Why it's specified like that, I will explain later, but for the moment it means I want to see the effect of a cell line, so how these different cell lines differ, and the effect of dexamethasone. And the effect of dexamethasone is the thing which I'm interested in, so I put it last. We'll see later why this is a useful way to do it. And now we've prepared everything. So far, everything we did is preparation. First, we needed to download our data. We needed to align our data. We needed to count, check for each of the alignment, whether they read, now that we know where it aligns, whether it falls into a feature, so into a gene. Then we needed to count the features to find out how often does how many reads fall onto a given gene in each of the samples. We needed a run table which tells us for each sample which cell line it was and which treatment it was. And now we can do the actual analysis. And the actual analysis is pretty unspectacular. It's just running this one command, which does now several steps. First, it estimates normalization constants, because some samples might be sequenced deeper and other less deep, and we need a scaling factor to make up for that. Next, it estimates the variance. We've talked already in the previous lessons about how important it is to estimate, to know how much things vary within group, so that you don't mistake random fluctuations for biological signal. And what this needs in this case, because we have 8 samples, 4 treated and 4 untreated, but each is a different cell line, we'll have to think a bit careful next time about what it actually means to ask for variation within group and between group. But for now, it has now fitted a model, and what model we fit we'll see in a moment, and produced results. And I can look at these results here. If I use them, I get a table like this, and this table has a couple of different columns. It tells us for each gene the average expression of this gene, the logarithmic fold change, so how much does the gene go up between dexamethasone treated and control, the standard error of the fold change. We talked a lot about standard errors earlier. The test statistic, it's the same as the t-statistic that we had last time. And what's the next thing? A p-value, which is associated with that, and an adjusted p-value. The adjustment is also something that is new and that we have to think about next time a bit. A first way to get an overview of what we have here is to make an MA plot in which we simply plot on the y-axis the log fold change, so the change from the ratio or the log ratio of the treated to the control samples, and on the x-axis we simply plot the gene expression strength. I put this here, and let's look at how this looks like. And here you see our gene, and the red ones are those which have a significant p-value, an adjusted p-value below 0.1. I don't want to explain now what adjustment means and so specifically, but these points here are, as you can see, there is nothing significant here for things which have less than, well, these are 10 counts, here are 1,000 counts, so this should be 100, this should be 1 count. So genes which have less than 3 counts on average are never significant. It's not so surprising. If a gene is expressed so weakly that we get only 3 or 4 reads in all of the samples among these millions of reads, the gene is probably too weakly expressed to say anything. So this is this big block here to the left. And now comes the expressed genes, and these seem to be the most strongly expressed genes. These little, they are drawn as triangles to indicate that they actually would be even further out. Important, these seem to be the most strongly expressed gene, and one important thing we have to talk later next week about is why they actually aren't. But nevertheless, everybody likes to go there, to look at them first. Yeah?
Okay, because it's written mean normalized counts. Can you explain further how normalization works?
Yes, probably not today, because we are already at the end. Yes, this is also on the list of things which we have to discuss about what we normalize here. The one thing that I show you quickly now is, let's have a look at this results table as it comes out. Here I have a results table, the gene ID, the base mean, the fold change, and all this. And to the very right I have my p-value, and here we have GPX3, which seems to be the most strongly expressed gene. Sorry, not the most strongly, the one with the most significant change. There will be, so how does this look like? And to do this, I now do the following. I take my, where is it? S-tipleronems gene, sorry, that was wrong here. This gene that we have here, let's go to the front. This has here this gene ID. I copy and paste it, and now I can look at them, at this thing here. Counts DDS is our count table, the one which we put in before, and you remember the count table has a row name, so I can use one of these as row names, and now it gives me here the counts for each of these things. Actually, I want the normalized counts to be able to account for sequencing depth. First calculate the size factors, so estimate size factors, details next time. So this is now the normalization procedure, which you might remember here when I ran the whole thing. Oops, up, sorry, up. Can't find it now. When I ran the DEC command, which did the whole analysis, it said estimating size factor, estimating dispersion, and so on. But you might remember I did it on my DDS DEXA object, the one with only the 8 samples which were not albuterons treated. DDS was the full thing with all of them where I haven't done it yet, so I have to do it normally. Now here I get now all these samples, all 16 samples, and the normalized expression of this gene. What I can now do to plot this, remember we have our sample table, our run table, and run, wasn't it called run table? Yeah. Our run table, which tells us for each of these 16 samples whether it's treated or not and what cell line it was. Let's add to this run table this thing here. And remember, we have this here. I add to the run table, mutate, and now add normalized counts. New column called normalized counts with this stuff. And now I have a table which contains, in addition, this stuff. So this is what I've done here. I took the run table and say I add one thing. And now I can give this thing to ggplot and do the thing which we've always done. I say I want a plot with points. On the x-axis, I want to see the treatment, whether it's dexamethasone treated or not. On the y-axis, I want to see the normalized count and the different colors for the different cell lines. And I want the y-axis log transformed. Invalid graphic states. I haven't seen that yet. So, and here it is. These are the points big enough for people to see, yes. So, as you can see here, it has sorted them a bit strangely. Untreated to the left, dexamethasone, then the treatment of both and albuterol. What we asked here when we did our analysis, we did the analysis only on the left, on these two samples, on the samples without albuterol. And there, as you can see, there is really a strong effect. It went up from around maybe 100 counts or maybe 30 counts up to 500 counts. From 30 to 500 seems to be a strong effect. Just to see how what kind of things we can expect, we can go back here and maybe choose one of these. You remember I've sorted this thing here by p-value, and let's go to something which has a still significant but not that great p-value. Let's go, this was too far down. These are all already non-significant p-value. Let's go somewhere here in the middle of the list. Bit higher. Here, p-value. So somewhere here, this is about what's just still significant. Let me take one of these genes here. This is the gene D-glucu. Probably some gluc, whatever it might be. And let's look at it. So I replace this here with something else. And zoom in. And now you see this is still sort of convincing, but it's a much less effect. You see, this time we go down from 80 counts to 40 counts. And it's not even clear if we would ask the blue cell line, when it would only be a change from 65 to 45. And who knows whether this is significant because other cell lines do much less. While the green one, that has a quite strong change. So this is something which people very rarely do, to actually look at a few of the hits. You get your results table, and you see which genes are strongly differentially expressed and which genes are weakly differentially expressed. And when people always ask, at what p-value should I cut off? Should I cut off at 10% or 5% or 20%? Well, if you look at something like this, then you can use your biological intuition and say, do I still believe that this is an effect that is relevant for my follow-up work, or it isn't? But if you never look at these plots, then you'll never know. So a very useful way is to be able to make such plots. So what's our work for next time? We need to discuss, of course, what actually happened when I ran this DE-seq thing. How does normalization work? What do we normalize for and what doesn't? We have to understand how the information of a cell line was used, how this dexamethasone thing, what the fold change actually means, how the p-values are calculated, what p-value adjustment means. The big problem is that if we were just to cut off p-values below 5%, we would get 5% of all the genes would always show up, no matter whether there was any effect or not. So we need to somehow safeguard against that. And what else do we need to look at? We should then, of course, also talk a bit how do you analyze more complex experiments, like like the dual interaction with dexamethasone and albuterol, both given together. And finally, of course, once we now have a list of genes which are upregulated, we have a list of genes. What do we do with that? How do we get biological sense out of this list of genes? Which is not so much statistics, but probably equally important. So, this is how far I got for today. I had hoped to get a bit further, but let's see. And I hope it was useful for you to get a quick overview of how this working on the command line works. The one point that I wanted to make maybe before I leave it, this what I've now shown you with first running the aligner, then running the feature count, and then loading into R. This is what people mean when they say set up an RNA-seq pipeline. So if you are a lab which is new to RNA-seq, people will tell you, yeah, but you first have to hire a PhD student to set up a pipeline, hire a bioinformatics PhD student to set up a pipeline. What this usually ends up is that you have somebody who spends months working on setting up some automated scripts which execute automatically these 3 commands that I've shown, right, for each of your files. Number 1, you can do it manually. Number 2, you should do it manually so that you know what's happening. Number 3, if you're really, now this is a bit because I've seen this happening quite often here at this campus. Number 3, if you're really, if a student really needs half a year to set up an automatization between of 3 commands, then obviously if this person wasn't the right one, probably didn't know more about how or wasn't really hired for the thing. And finally, how the hell are you supposed to write your PhD thesis about I've automated something? The way how you do it is by saying I've set up a pipeline. So we'll come back to this afterwards, but there is huge problem with these concepts of a pipeline where somebody sets up something which is easily described, can easily be done manually, only with the effect that in the end you don't know what happened. And in the end you get out a final list of genes and you're not even able to do plots like this. So I want to show you now, for now it maybe didn't look like it's easy, but because I rushed a bit through it, and you have to rush a bit because if you want to show it slowly, then you always have to wait for the computer to actually do it, and that takes half a day. But the whole difficulty in working with high throughput sequencing data does not lie in setting up the programs, buying a powerful enough computer, aligning the stuff, and so on. That's something that any competent person should be able to get done quickly. And if it appears to do this big, this is usually, sorry to say that, most of the time a supervision failure. Because there's too many PIs who think, this is maybe a warning for the PhD students here in the room, if your PI hired you for the explicit point of doing a job that nobody else in the group knows how to do, like a wet lab group hiring a bioinformatician PhD student to set up their thing, then this is bound to fail because nobody can supervise the student. And so if you find yourself in this thing and you're a postdoc, that's fine. You're now a grown scientist, you should know how to do it. If you're a PhD student, then somebody is exploiting you. Yeah, that was my, as we say in German, Wort zum Sonntag, the general sermon. But finally, the important part, which gets really difficult, is what we haven't touched today, what we'll do next time. How do we actually get math out of that? Okay. Aber das ist fast immer erstaunlich viel Arbeit.
Ja, aber das wird sogar mal erklären,
Ja.
anzugucken. Aber das,
Ja. Wieso mag das Ding nicht? Jetzt. Was mache ich denn da jetzt? Trends in Kids and Parenting this week. Was?
Was ist da bist du da gelandet?
Das ist die. Was ist denn jetzt?